All right. Oh, say it louder. There you go. Okay, so today we're going to be doing section 6.4, and 6.4 is where we start to really mix our trig with our vectors. But before I actually start section 6.4, I wanted to just go over some basic things, make sure that we can all agree on some basic concepts. Cool? Yeah. Cool, great. All right, so just going to draw a standard coordinate grid like that. Well, not even grid, quadrantals. And I want to throw vector, and you don't have to draw any of this. I want to throw vector 3, 4 on it. Can we all agree that the vector 3, 4 is in quadrant 1? Because, okay, cool. Picture not drawn to scale. Never is. But we're going to say there's vector 3, 4, just like that. And because I chose 3 and 4, I hope that we can all agree that its magnitude would be 5, because it would form a 3, 4, 5 right triangle. Okay. So this vector has length of 5, but specifically points towards that coordinate, right? Great. Let me ask you then, which quadrant is this one in? Quadrant 3. Well, that would be another 3, 4, 5 right triangle, wouldn't it?
That would be.
So then what relationship do these two vectors have?
Same.
They do have the same magnitude, but what's their relationship to one another?
Oh, they're parallel.
They're parallel. Now I know that they're end to end, but they're parallel. But what do you notice about the red vector when you compare it to the blue vector? Well, that's just because my drawing is poor. Yeah, picture not drawn to scale because I'm not an artist. How could I get the red vector from the blue vector? A scalar multiplier of -1. We've already talked about what a negative sign on the front of a vector does, right? That basically makes the vector point the exact opposite direction, right? So vector, well, I didn't name it, the red vector is the blue vector times -1, right? And they have the same length, right? Great. One more question. What is the angle between these two vectors? 180 degrees. Of course, in radians would be pi radians. So we understand now that putting a negative sign on the front of a vector creates a different vector that's exactly 180 degrees or pi radians away, right? And they make a straight line. How about that? Time to introduce you to the polar coordinate system. The Cartesian coordinate system is what you're used to, x, y. It's also called rectangular coordinates, and I hope it's obvious why, because every time you've seen a piece of graph paper, it's full of squares, right? They're called rectangular because there's a bunch of up, down, and left, right. That makes rectangles. Well, of course there's other ways to graph things. Polar coordinates graph things in circles instead of in rectangles. Instead of an x, y, our polar coordinate system is made up of r, theta, where r is the length of a radius and theta, well, I think it's kind of obvious. It's an angle. And just like trigonometry, positive angles open counterclockwise, negative angles open clockwise. Nothing different here, okay? So we call the positive x-axis the polar x-axis. We still call this a terminal side. We don't say origin anymore. We say the pole, P-O-L-E, okay? So this could represent a vector OP if we wanted it to. Begins at the origin, pole, ends at point P. Cool with that? So instead of saying it's x, y, we could say it's r, theta. It's this far away from the pole, and I had to turn that many degrees to get there. Cool with that? All right. Well, if you think of r as being specifically a directed distance, like a vector, that actually opens the door for things like negative radius. Now, when we were doing trig, I told you that the radius is always positive, right? Well, that's because we didn't know the polar coordinate system yet. Technically, the radius can be negative in the polar coordinate system, but you guys just saw what happens to a vector when you put a negative sign in front of it. It turns it 180 degrees, pi radians away, forming a straight line. And that's what you see happening here. This is the point r comma theta. It is r away from the pole at an angle of theta. This one is exactly 180 degrees away. So we could say this is negative r comma theta. Just makes it point the opposite direction. Now it's not the same, and it's the same theta. It is. It's the same theta. Theta tells you the degrees you would have turned, and then r positive says stay on that line. R negative says, nah, go the other way. And it'll make a lot more sense when we actually practice it. Polar coordinate system, like I said, is made up of circles, not rectangles. When I graph polar coordinates, I always pay attention to the angle first. I decide where I want to draw my ray, and then I ask, is that a positive radius or a negative radius? If it's a positive radius, I draw the ray. If it's a negative radius, I draw a dotted ray and go exactly 180 degrees the other direction. This one is just 4 comma pi over 3. So I'm going to say pi over 3. I like to look at that first. That is here. And 4 means it is 4 rings away from the pole. So 1, 2, 3, 4. I put the point, and I go, oh, is it a positive radius? Oh, it is. Then that is point P. If the radius had been negative, that would have been a dotted blue line, and I would have actually drawn P down here. Let's see, where am I? Down this line, right there. Okay. Is this the only way to get to point P? No. There's an infinite number of ways that you can get to point P. Just like in trigonometry, if you turn a full 2 pi in either direction, you're going to be in the same spot. So I can add 2 pi to my theta, I'll land here. I can subtract 2 pi from my theta, I'll land here. Things like that. There's also ways to play with the symbol in front of the radius. We'll get to that in a minute. Let's do this one. Different color. Red. I track the angle 3 pi over 4. 3 pi over 4 puts me here-ish. Yep, right there. And now I count the rings. This does say 6 rings. 1, 2, 3, 4, 5, 6. If the radius was positive, that is where that would have gone. But that radius is not positive. That radius is negative. So my job is to reflect it 180 degrees, pi radians, to create a straight line and go 6 rings in the exact opposite direction. 6. There we go. There is point Q. So the angle told me which way to look. I count out to 6 rings, and the radius tells me either stay here or reflect 180 degrees away.
We have to put the dotted.
You should put the dotted. Have to? No. Should you? Oh yeah. You really want to be doing
For later.
for always. Okay?
No.
What?
I said just so you know.
Oh, just so you know. I thought you said just so you don't. And I was like, I don't understand.
Can't you just do it like 3, or can't you do like 6, 7, or like 6 comma 7 pi over 4?
So
Or no?
Kelly is asking, could I have written this with a positive radius and changed the theta? Of course we could. Because if I wanted to say it was positive radius 6, then I could have gone all the way to 7 pi over 4. Or positive 6 comma negative pi over 4. So of course, there's an infinite number of ways you can change the symbol on r, or you can change the symbol on theta to get to the same point. And we're going to practice getting multiple answers from the exact same coordinate in just a moment. But yes, of course we could. And the last one I'll do in green, that is 3 comma negative 75. That one's actually in degrees. Negative 75 degrees, well, that means go clockwise. That's all that means. So go clockwise 75 degrees, which is basically the same thing as saying 360 minus 75. What is it? 285. So we go down to 285 and we count out 3 rings. 1, 2, 3. We ask ourselves, is that positive or negative radius? It's positive radius, so no reflecting. You just throw it on there. And that one is point R. So there are always a minimum of 4 ways to write these things out. There is your standard r theta. Then there's a negative r theta. There's r negative theta. And of course, negative r, negative theta. And we will be well versed in finding all of those. I'm just going to go ahead and tell you right now that you do have a test question that says, select all of the coordinates that are in the same place as this one. So I give you a polar coordinate, and then your job is to go through the multi-select question and select all the other ones that are the exact same point. And this is how you do it. Cool? Yes? No? Maybe so? Good? Okay. So let's practice getting the multiple versions. And I added an example to this first period, so don't take up the whole space. Take up like half of it vertically, and I'm going to add an extra secondary question. There we go. If point P has polar coordinates 3 comma pi thirds, it says find 2 more. No, we're going to do better. We're going to find 3 more. That way we can get all 4 versions. That way we can move the negative sign to all the letters if we want to. 3 comma pi over 3.
Wait, so if on the test, if you give us polar coordinates, right?
Mm-hmm.
Then you gave us one set of polar coordinates, then the max we can find is 3 more.
No. Because you could always turn 2 pi and you'd land in the same spot. Okay. Anyway, picture not drawn to scale, but we need to draw a vector directed distance, 3 at angle pi over 3. That's going to put me in quadrant 1, right? These are both positive. So this is actually my positive r, positive theta. We're only going to find the other 3. Picture not drawn to scale. I'm too lazy. See, we know positive r, positive theta. What color did I do next? Was it green? Yeah, negative theta, or negative r, comma theta. So negative r says it would have pointed the other direction, and we want to put those as dotted lines. That would have been out here then. So if we want to use this point, and we want to use this one because it'll have negative radius, what theta gets us there?
4 pi.
Not negative yet. Wait on that one.
Isn't it?
Yeah, it's 4 pi over 3. And the reason why we know that is because this is a pi over 3, so this is a pi over 3. This is a pi over 3 after pi.
I just thought of the 180. Like
That
pi.
too. Yeah, because you added pi to it. So this green one is going to be negative 3, comma 4 pi over 3. And then the next color I used was purple. Now because it's positive r, I want to land on the solid ray. I want to land here. How can I get to here with a negative angle? So start here and go a negative angle, which means go clockwise. How far do I have to go around? Yeah, I had a lot of people say it. Negative 5 pi over 3. It's basically this number minus 2 pi. Because every time you add or subtract a 2 pi, you land in the same spot. But if you subtract a 2 pi from this, you have turned a negative full circle. And then lastly, I did both negative. Both negative means land here, but use a negative angle. And you were going to give it to me a little bit ago. So this angle is negative pi over 3 is here. So if I wanted to do this, to get a negative angle, how far do I have to go to get from there to there? There you go, negative 2 pi over 3. And because this is dotted, we already know our radius is negative. So it's negative 3 comma negative 2 pi over 3. Just like that. Pretty cool, huh? So if you don't draw the dotted line, like you were asking, this I struggle. I'm a visual learner. I really am. There's no such thing. But I really do need to see the images. It helps. I can't visualize this. I have to actually see it.
Wait, what does it exist?
Different types of learners. There's neuroscience that shows that there's no such thing. Anywho, let's do I have time to add another example? I do. I have time to add another example. Let's throw another one up there. And I'll try to keep the same color scheme. Only this time, let's see, going to make the point, the coordinate, negative 2 comma 3 pi over 4. So that one's actually my green one. That's my green one. The first thing we need to do, though, is figure out where that is. So 3 pi over 4 puts us where? Right, so quadrant 2. So 3 pi over 4 puts us in quadrant 2. Negative radius puts us across it, so we'd be in quadrant 4. So this thing is actually going to be over here. Because negative radius tells you point the exact opposite direction. This put us in quadrant 2. That reflected us to quadrant 4. We went exactly pi radians or 180 degrees from where the angle told us to go. And now we're just going to fill in the other ones. Blue for last time was positive, positive. So let's go with positive, positive. Positive r means we land on the solid ray. Positive theta means we needed to have started at 0 and went counterclockwise. Or you could start here and go counterclockwise 2 pi. Either way, you're going to get the same result. So start here and go all the way around to here. How far is that? 5 pi over 4 is over here. There we go. 7 pi over 4. Because it's a pi over 4 before 2 pi. You could have just done, you could have said this was negative 3 pi over 4. Oops, I just told you what negative theta is. So in purple, r would mean we landed here. And then negative theta means we started at 0 and just went clockwise.
So R and theta is both positive. That's the same 360.
No, if r and theta are both positive, that means that you're landing exactly where theta says you should land. And positive means you were moving clockwise. So if I say positive r but negative theta, that means start here, land on this, and go clockwise. Because this is negative r, this is positive r. And then the last one would have been both negative. Negative theta means you're turning clockwise. Negative r means you're landing on the dotted ray. So start here, go clockwise to here. We already know it's going to be -2 as the radius, but what negative angle gets you to here from here? -5 pi over 4. Which part? Everything starts at 0. And turning clockwise is negative angles. Turning clockwise or counterclockwise is positive angles. Landing here is negative radius. Landing here is positive radius. Because the negative radius just says reflect away from where theta told you to be. The dot. You're reflecting from the quadrant. This said, go to quadrant 2. And this said, lol, reflect to quadrant 4. If that had said +2, we would have stayed right there and we would have made this a solid line. But because it was negative, we had to reflect it. Why is this -5 pi over 4? Because if you go clockwise, this is -pi, which is -4 over 4, and then there's another 1/4. Because if from here to here was 3/4, there's still a 1/4 here. Good? Okay. It'll be much easier with a lot more practice. Just you'll see. So how do we find all the polar coordinates? Well, like I said, there's an infinite number of correct answers. I don't want you trying to memorize this setup. I want you to understand the setup. If I give you an r comma theta and I want tons of answers that all have positive or negative angles but keep a positive radius, I can just turn full circles, right? Turning a full circle in either direction lands me in the exact same space, right? So that's plus or minus whole circles. How many circles? I don't care. Which direction? I don't care. You're going to land on the exact same place. The n, that just means number of circles. So n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It doesn't matter. And then plus or minus because it doesn't matter which way you turn. But what if you want negative radius? How far away is the point if I use negative radius from the point when it has positive radius? Pi, or 180 degrees. Let's use radians though. It's pi away. But hold on. Do not write theta plus or minus pi in. Because every even one would allow this. And that wouldn't be the same thing. We need to make sure that we only have odd pi's being added and subtracting. Do you know how to list odd numbers with using an n? Like I did. This lists all the even numbers. 2n lists everything even. Do you know how to list odds? No. You just add 1. It's 2n plus 1. Or 2n minus 1. This will guarantee that every number inside those parentheses is odd. I don't want you trying to memorize this. I want you to understand what it says. Because I forgot. Good catch. Get skinny, math. Yeah, completely forgot to write theta. It just means go a half circle away from where you were. That's all it means. I don't want you memorizing it. If you can draw them and then see, oh, I want to land on the negative radius, or I want to land on the positive radius, you're fine. I don't even have these memorized. I don't want to. So if I told you that there's this whole new coordinate system called polar coordinates, and there's actually a lot more than that as well. So when you step up to 3 dimensions, a lot more things get introduced. In 3 dimensions, we have the x, y, z, still Cartesian, kind of like cartography. It's like map making. It's Cartesians, x, comma, y, comma, z in 3 dimensions. We still call them, they're like cubic coordinates. R, theta, and phi would be spherical coordinates. And then there's also cylindrical coordinates, where you have radius, height, and theta. Or no, not height. You have radius. Oh boy, it's been a long time since Calc 3. Well, there's spherical coordinates. I'm struggling right now. There's also conic coordinates, where it's all from cones. I mean, it's wild. There's a lot of really crazy stuff. What do we use coordinate? Well, think about it like this. If I needed to have your exact location on this planet, is our planet a cube or a sphere?
It's not even a sphere.
Well, spherical though, right? So the most accurate coordinate system that we can give in 3 dimensions would probably be, and the easiest to understand, would be spherical. It's slightly, it's kind of oblong. It's a little bit egg-shaped. I don't know, to be honest with you. I've never done the math that required cone coordinates. They do have use, though. I just never done the math. I've done Cartesian, spherical, and cylindrical. I've never done conic, but I do know it exists. See, a lot of navigation, especially for like our satellites and stuff, they use spherical coordinates because they're just really easy to work with in space. So if these coordinate systems exist, does that mean that they exist, apart from each other? Of course not. If I can put this point right here and give it an r theta, I feel like I could also give it an x comma y, right? Yeah, you can. I mean, we already know how long the hypotenuse is. It's 2. And since we know that this is 3 pi over 4, couldn't we just use trigonometry to get the x and the y? Of course we could. What that means is there are ways to move backwards and forwards between polar and Cartesian, just using the trig that we already know and love. You see, sine of theta is y over r. That's true for vectors and for trig, and true for everything else. So if you multiply both sides by r, you get that y equals r sine theta. Cosines x over r. X equals r sine theta. Tangent of theta is y over x. It just is. And then we've got the equation of a circle, x squared plus y squared equals r squared. Pythagorean theorem. Oh, I've already said that. We can use these 4 identities to convert backwards and forwards between polar and Cartesian. So let's do that. Quick question. Yeah, what's up?
Yeah, so you're getting that x equals r cos theta.
Yes.
From the cos theta equals x over r.
Right. You just multiply both sides by r.
Right. So what happens if there's a negative? Would we still multiply by negative r?
So if you had negative r, that would reflect you to somewhere else, right?
Yeah.
And if you asked me to convert that to x comma y,
yeah,
I would just use these and use positive r.
Okay.
Now, if I wanted to, I could use that, and then have negative r, but that's kind of like extra. Basically, you're just going to do the easy thing.
So I'm going to make it into positive r.
Yes, and here's why. There's an infinite number of ways, because of trigonometry, to write every polar coordinate. That's not true for x comma y.
Yeah.
And xy is an xy, and there's nothing much you can do about it. So you would basically just go, well, where is positive r? And you go from there. Okay, that's a good question. I don't think anybody's ever asked me that before. So here we have two polar coordinates, and we are going to convert them to Cartesian coordinates. I draw everything. I draw everything because I don't do very well with pictures in my head. Luckily, positive radius, because it's really kind of a pain in the butt if it's negative radius. I feel like I should do a negative radius question just to demonstrate. If I have time, we'll throw example C on there. But for now, let's get this. Positive radius with an angle of 5 pi over 6. Which quadrant is that? Quadrant 2. Quadrant 2. Picture not drawn to scale. Never is. Trying to pick a good color. Positive radius. And we know that the angle is 5 pi over 6. So then what's left inside this triangle? A pi over 6, and in degrees is 30 degrees. Well, that looks like 300. Look, it's just a 30, 60, 90 triangle. There's always a 1 across from a 30, and there's a root 3 next to a 30, but because I'm in quadrant 2, that must be negative. There. We're ready to rock and roll. Yes? Okay, yeah, so it should be a 2. I put a 3 there because it has a length of 3. Tell you what, we'll get to that in just a second. So these are the numbers for the special right triangle. Good catch, right? Because x is r cosine theta, where r is 3. You guys, sorry about that. This. He's looking at me like, what the heck are you saying? X is r cosine theta, right? Okay. This was just me drawing the triangle for 5 pi over 6, not necessarily with the 3. I wrote it by accident. Okay, so I just wanted the 5 pi over 6 triangle so I could do cosine and sine there because I don't have my unit circle memorized. Okay. X is r cosine theta. So for us, that is going to be 3 times cosine x over r, negative root 3 over 2. And y is r sine theta. That's 3 times y over r, 1/2. So the Cartesian coordinates for point P are negative 3 root 3 divided by 2, comma 1 divided by 2. Ta-da! R cosine theta, r sine theta. Don't shake your head no back there. I see you. What are you shaking your head no about?
Isn't it like 3 over 2?
Oh. You know, 3 times 1/2 is 1/2. Or 3/2, I mean. Yeah, what's up? I'm sorry? No, it matters. It's right here. So the triangles, because I don't know my unit circle, the triangles that I draw, one's going to have a radius of root 2, and the other's, and let's say hypotenuse for these questions, because radius means something different in polar coordinates. My hypotenuse is either going to be a root 2 or a 2, because that's how I do my trig. So this is just my 5 pi over 6 reference triangle. That's all this is. The formula for the x Cartesian coordinate is r times cosine of theta. So it's the 3 of this polar coordinate, and then cosine of this angle. I need this triangle to actually find cosine and sine. I don't have them memorized. Let's do that one. Let's do that one. Black, point Q. Where is negative 200 degrees? Which quadrant is that? Negative 200 degrees. Positive 200 degrees is quadrant 3. It's quadrant 2 again. Tell you what. And it also says positive radius. Is this going to be one of our special angles? No, it's not. Because it's like a 20-degree reference angle, right? This is negative 200 degrees. There's not even a reason to make a triangle. Because it's not special. We're going to have to use our calculator. X equals R cosine theta. You just type it. Y equals R sine theta. Now, I don't have these numbers memorized, so time to grab a graphic calculator. Make sure I'm in degree mode. I am. 2 cosine negative 200. Aha. So the coordinates will be negative 1.88, comma, 0.684. There. And I kind of want to answer Zach's question, and I want to throw an example C on here, one with a negative radius, just so we can see what happens. All right? And we'll use a positive theta. So negative radius, positive theta. Positive theta, being pi over 4, wants us to be in quadrant 1. The negative radius tells us to reflect out of quadrant 1 into quadrant 3. But pi over 4s are my special angles. Can we agree to that? One person said yes. So if we were going to do it, I'm going to make it really small. There's the negative radius version, which means it better be down here somewhere, like that. Now I'm going to, oops, spray my shoestring over. Now I'm going to draw a special right triangle in quadrant 3 with this as my reference angle because, again, I don't have my trigonometry memorized. No shame in that game. What kind of reference angle is a pi over 4? 45 degrees. That makes this a 1, 1, root 2 triangle. But since I'm in quadrant 3, both legs are negative. X equals R actual radius from the polar coordinate cosine of theta. Y equals R sine theta. I'm sorry? Yes, but the reason why I drew the picture is because I wanted you guys to see what this would look like. We know that this xy had better be negative x, negative y, right? Because you're in quadrant 3, where both x and y are negative. He was asking what happens if there's a negative radius. Well, the negative radius puts me here, so negative x, negative y. But if I do cosine and sine, both of these equal 1 over root 2. So both coordinates are negative 4 over root 2. So to answer your question, Zach, I could either use this. He's not looking.
Yeah.
I could either use this special right triangle with negative radius 4 and angle positive pi over 4, or I could use this one where theta wouldn't have been pi over 4, it would have been 5 pi over 4. Do you see that? that where this is actually at 5 pi over 4. So I'll either do this triangle at 5 pi over 4, or I do this triangle at pi over 4, positive radius, negative radius. Hopefully this video worked.